So welcome everyone to the keynote on our last day of Sigma. I'm very pleased to introduce our keynote speaker, Wang Tan, who's at Facebook AI. And her keynote speech will be about deep data integration, which is a topic that we would all like to learn more about. So Wang Chu is somebody I think of as one of the experts in our community in the area of data integration, as well as sort of looking at data exchange, data provenance, a variety of topics that are very central to our community. She is one of the, I would say, one of the unique people in our community who is very active in SIGMOD, and yet her work has been awarded some of the highest prizes from the database theory community. She's a co-recipient of the 2014 ACM Pod's Alberto Mendelsohn Test of Time Award, the 2018 ICDT Test of Time Award, and the 2020 Alonso Church Award. She was also a recipient of the 2019 VLDB Women in Database Research Award and is a fellow of the ACM, and is somebody who has spent time in both academia at the University of California, Santa Cruz, as well as multiple companies, ranging from IBM Research to Megagon Labs and now Facebook. I think the diversity of her experience is something that we can all learn from. So Wang Chu, welcome, and we look forward to listening to your talk. So please go ahead and play Wang Chu's talk.
Good morning, good afternoon, good evening, everyone. Thank you for taking time to attend this talk. I'll be talking about deep data integration, more specifically on the topic of how deep learning has been applied to data integration problems in recent years. So first of all, what is data integration? The goal of data integration is to provide uniform access to different data sources. That is, if data integration is done right, the user gets the illusion that she's accessing only one data source, even though there may be several underlying data sources in different formats. So she does not know, for example, she's accessing 5 different data sources, and there are multiple columns across different data sources with the same name but different meaning, or different names but same meaning. So she does not need to know that some values are missing from some columns of some data sources. Traditionally, there are 2 approaches to data integration. The first one is called virtual data integration, also sometimes known as data federation. The second one is the data warehouse approach. And today, many of you may have heard about data lakes as well. Schematically, this is how a virtual data integration system looks like. There is a number of data sources on the left, and there is a global schema that presents to the user a uniform view of how the underlying data sources look like. That is, what the user sees a single schema and queries the underlying data sources through this single schema. And she's unaware that, in fact, multiple underlying data sources exist. When a user poses a query against the global schema, the query will have to be rewritten to possibly many different queries against each individual data source to retrieve the relevant data. And the results will have to be massaged to put back into a form that can be returned to the users as answers. Here, no data actually exists under the global schema, but it appears to the user that the data is integrated, hence the name, the given name, virtual data integration. A data warehouse is similar, except that the relevant data from the sources are brought together as a single data source, called the data warehouse, that conforms to the global schema. That is, the schema of the data warehouse provides a uniform view of the underlying data sources, just as in the case of a virtual data integration system. When a user poses a query against the schema of the data warehouse, this query can be immediately answered using the data warehouse alone. A data lake is simply a collection, usually a massive collection of raw data sources. The data sources may or may not have a schema. They can be of different formats and they can reside in different locations. Just like in virtual data integration and data warehouse, one of the main challenges for a data lake is how can we query the data, in this case, data in the data lake. To do this, we need to understand how to do data discovery, extraction, cleaning, and integration dynamically over the data lake. In fact, all these problems also exist for virtual data integration and data warehouse. Those pictures that I've shown you earlier, they don't tell the whole story. It's just that in the former two cases, a lot of work on data discovery, extraction, cleaning, they were already done before query answering takes place. Whether it is virtual data integration, data warehouse, or data lake, to bring the relevant data together to a state where a query can be answered, there are typically many steps involved. In other words, data integration is an ecosystem consisting of many steps or tasks. Well, first, how do we identify what are the relevant data sources? And these sources may be unstructured and in different formats, and they can be of different modalities. So how do we manage all these differences? How do we identify and extract the relevant information from these data sources? How do we understand how different sources are related, and how can we specify the precise relationship between them? This will be important for understanding how, for example, to transform the needed data from one format into another, for example, into one that conforms to the global schema, so that the user query can be answered. Very often, we also have to understand how to deduplicate entities in the same source or from different sources, and how to consolidate information coming from different sources together, and to deal with missing values, dirty data at the same time. So the data integration ecosystem encompasses all these different tasks and is sometimes also called data preparation and integration. Each of these are very important steps in the whole data integration ecosystem. So I've already given you an overview of the data integration ecosystem. I'll provide an overview of deep learning next in a few slides, just enough to get us to do a deeper dive into one example data integration task, which is entity matching. In this deeper dive with entity matching, my goal is to show how a specific type of deep learning technique, which is transformer-based pre-trained language models, can be applied to entity matching. After this, I would like to take a step back to discuss why deep learning techniques have been so successful in data integration problems, and what I believe are some of the interesting challenges and opportunities for the data management community. So first, deep learning algorithms are a type of machine learning algorithms based on neural networks. And very briefly, a neural network looks like what is shown here. It has an input layer of neurons, two or more hidden layers of neurons, and an output layer. The input layer takes a numerical representation of data, and the output layer returns an answer. Deep learning techniques simply refers to neural networks with typically several hidden layers, and hence the name deep in this sense. Deep neural networks are meant to mimic the way a human brain functions, where the neurons are connected together in complex ways. Now, here is a magnified view of a neuron, where you see on the left inputs coming in to the neuron, and on the right an activation function out of the neuron. In our standard logic circuits, the activation function is a step function that will result in 0 or 1. In the case of general neural networks, they are typically nonlinear functions, which takes as input the weighted sum of inputs together with a bias. Nonlinear functions make them more sophisticated and more expressive in general. Information is passed between network layers through the activation function. The weight and bias parameters, which are represented by W and B, respectively in the activation function, are tunable and are adjusted during the learning process of a deep learning algorithm based on the training data it receives. So what happens is that during the training time or the learning time, the network backtracks through all the layers, and this is called a backpropagation phase, to update the W's and B's of every neuron. The goal is to minimize a loss function, so every iteration of backpropagation typically results in a smaller loss, and then over time, the model learns the right W's and B's to approximate the relationship between the input and the corresponding expected output. Now, with that in mind, you can imagine there are lots of different types of neural networks out there just based on the topology of the neural network alone. This is a web page called the Network Zoo, which curates and explains the different neural networks out there. And this chart here is already outdated. I won't be going into the details of these different neural networks because I'm not an expert myself, and that's not my goal. But what I want to do is to get some understanding of what are transformer-based pre-trained language models, which has been getting very popular these days for many natural language processing tasks, and recently data integration tasks as well. There are a number of neural network architectures that ultimately led to the development of the transformer model, which is the basic building block of many pre-trained language models we see today, such as BERT. The paper that got all the attention in NeurIPS 2017 is this one titled "Attention is All You Need," that described the transformer architecture. As you can see, the transformer model is built on top of ideas from several prior neural network architectures shown here. At a high level, a transformer model possesses the following useful properties. It has self-attention mechanism, which means it is able to relate a word or token to its neighboring tokens, whether the tokens are on the left or on the right of the word. In other words, it is able to contextualize the meaning of a token, and is also very good at capturing longer range dependencies between tokens in language understanding. Let's take a look at the following two example sentences. For static word embeddings such as glove or word to vec, the word bank will have the same embedding for both cases, for both sentences. However, for transformer-based models like BERT, the embedding of the word bank is different for both sentences because the embeddings of the word bank is dependent on its neighboring words. The second property is that it has multi-head attention, which means it can relate a word to its neighboring words based on different relations, different semantics. For example, it may be the subject-verb relation for one head and the pronoun-noun antecedent relation that is captured by another head. In other words, it's able to take different views or understanding of language. The third is that self-attention is permutation invariant to the order of tokens, but as we know, language is inherently sequential in nature. In the Transformers paper, they also propose how to encode the positions of token through a neat positional embedding trick to indicate the relative word positions. There are a couple of other neat tricks described in the paper that I won't go into details, but the short story here is that transformers are used to develop what we now know today as pre-trained language models, such as BERT. Okay, so now we're all experts in transformers. Let's see how this is used in BERT to build BERT, which is a very popular transformer-based pre-trained language model. BERT uses bidirectional layers of transformers, and this is shown in the diagram here. It takes an entire sequence of tokens as input simultaneously and passes them through the transformers. Each transformer feeds forward to every other transformer in the next layer. And in the final layer, we obtain the output, one from each transformer. For example, the BERT-based model has 12 layers of transformers all interconnected. and the BERT large model has 24 such layers. The BERT model has become very popular because it offers a fine-tuning paradigm for many different downstream natural language processing tasks without needing to change the architecture at all. That is, different downstream tasks can all benefit from the same pre-trained model. So what does pre-trained model mean, right? The BERT model is pre-trained on two unsupervised tasks, hence the name pre-training, the title of the paper, using two data sets, the book corpus and the English version of Wikipedia. The first task is called a mass language model task, where some tokens of sentences are randomly removed, and the model is asked to predict the missing tokens. The other task, the next sentence prediction task, asks the model to predict whether, given two sentences, whether the one sentence follows the other. A number of positive and negative examples of the next sentence prediction tasks are generated based on the data sets and used to train the BERT model. BERT is one of the earlier transformer-based pre-trained language model. There were earlier pre-trained models such as Elmo, but BERT's architecture was just simple and makes it easy for reusing the pre-trained model for different downstream tasks. When it first came out in 2019, it was already beating the state-of-the-art techniques on several natural language processing benchmarks with pretty impressive gains. In recent years, we have seen a proliferation in the number of transformer-based pre-trained language models, and I'm just showing some of them here. Every new one tends to perform better than the previous, and they tend to be developed with specific goals in mind. For example, the GPT family targets sequence generation, while DistillBERT is developed with a smaller memory footprint in mind. As I've mentioned several times by now, one of the reasons why pre-trained language models are so popular, besides being already powerful out of the box, is that these models are also easy to fine-tune, and they tend to perform even better after fine-tuning on application-specific tasks. In recent years, we have also started to see many applications of pre-trained language models on data integration tasks as well. I will show you an example of how a language model can be fine-tuned to work for data integration problem, in this case, the entity matching problem, next. So let me switch gears a little to tell you about the entity matching problem first, before showing you how one can use a pre-trained language model to solve the entity matching problem. So first, what is the entity matching problem? The entity matching problem is as follows. Given two data sources, the goal is to find all pairs of entities, one from each data source, that are actually referring to the same entity. In other words, we would like to output all pairs of entries, one from each data source, that refer to the same product or the same company or the same person. This sounds like a really simple problem, right? Well, except that it's not. Just imagine if you have 1 million records in one table and 1 million records in another table, you end up with 1 trillion records to compare. And I'll come back to this point in a bit. The other issue in entity matching is that once you have a candidate pair of records to match, we also have to understand how to judge when two candidate pairs match or not. And this can be a very tricky issue itself. Entity matching is one of the more prevalent problems in data integration. Chances are that if you need to deduplicate data, do knowledge-based construction, or entity search, you will need to use entity matching solutions at some point. It is also not a new problem. It has been around, it going as far back as the paper by Feligi and Santer on a theory for record linkage, which is published in 1969. So actually this is more than 50 years ago. So given that entity matching has been around, it is not surprising that entity matching is also known by many different names, such as entity resolution, entity record linkage, reference reconciliation, and duplicate detection. As Guru Jada et al. In their CIKM 2019 paper stated, is an interesting remark. Well, they said that perhaps the name itself needs entity resolution. In the next few slides, I'll walk through the system Detour, which is an entity matching system built on pre-trained language models. This is joint work with Yuliang Li, Jinfeng Li, and Yoshi Suhara from Megagon Labs, and An Haiduan from University of Wisconsin. This work is going to appear in VLDB this year in the Scalable Data Science track. So typically, entity matching systems take as input two data sources of the same type, but Detour does not have this requirement. For example, the input to Detour in one collection can be a relational table, and the other can be a JSON file, for example. It returns all pairs of entries that refer to the same real-world entity, such as a product or a company. And here are two collections of data, two tables in this case, where one table has 3 columns and the other table has 2 columns. And the goal is to find out which pairs, one from each table, refer to the same real-world entity. To solve the entity matching problem, the work is typically divided into 2 phases. The first phase is called the blocking phase. The goal of blocking is to reduce the number of pairwise comparisons needed to in the next phase, which is called the matching phase. Now, recall earlier that I mentioned that if you have 1 million tuples in each table, you end up with 1 trillion pairs to compare. This does not work. It's not practical. So the blocking process is intended to reduce the number of pairs to consider, so that in the matching phase, we don't have the case of 1 trillion pairs to compare. The blocking phase typically uses simple heuristics. So an example heuristic we can use here for these 2 tables could be that viable candidate pairs must share at least 1 token in the title. If we apply these heuristics, instead of 9 pairs that we have to compare, we are immediately reduced to these 3 pairs shown in dotted arrows here. These days, there are also blocking techniques that uses deep learning, for example, to find similar pairs based on the similarity of the embeddings of the pairs. And in practice, the main requirement of the blocking function is that it needs to run really fast and have high recall. And in the blocking phase, it's okay for the precision to be a bit low. The next phase, the matching phase, which is what I'll focus on in this talk, right, is the phase where precision needs to be high. So entity matching is a challenging problem. Out of these 3 candidate pairs shown here, only 2 of them are true matches. In all these cases, the state-of-the-art entity matching solutions around April last year failed to correctly make the match or non-match decisions. The examples here illustrate the challenges that exist in the matching decision. Right. First, language plays a crucial role, especially for text-heavy data. There is quite a bit of text here in the title columns of both tables. Second, knowing what to pay attention to when making matching decisions is also important. And what you pay attention to can vary from pair to pair. So there are no fixed rules at all. So in this case, in the second pair, we somehow need to know that the addition number is important here for making the non-match decision. And in the third pair here, right, the model number, even though one is found in a model column and the other is part of the text, is important here for making the match decision. The last example also suggests that it is important for one to be able to handle dirty data. And in this case, the model number is sitting nicely in one column in the first table, but is part of the text in the second table, right? And dirty data is very common in real-world data sets. And dirty data can also mean missing values, corrupted values, values with irregular structure, in addition to the misplaced information as shown by this example. So now let's go back to fine-tuning. Detour fine-tunes pre-trained language model for entity matching. Recall that pre-trained language models are already trained on large data sets. For example, BERT is trained on the book corpus and English Wikipedia, and they, without fine-tuning, already establish strong baselines for several NLP tasks. The architecture of pre-trained language models such as BERT makes it very easy to fine-tune the model for different applications, and is often cheaper to fine-tune a pre-trained language model with labeled data for your own needs than to pre-train a language model from scratch. So what does fine-tuning actually mean? Recall that there are several layers in a pre-trained language model. Fine-tuning simply means freezing some layers and train on the remaining layers. Train on the remaining layers means adjusting the weights and biases through the training process on new labeled data. A typical approach is, for example, to actually freeze all the layers and then attach new layers on top of the model, and then train the weights of the new layers based on the labeled data for your task at hand. So let's get more concrete than that. In Detour, for example, we attach a linear layer on top of the BERT model before passing it through the softmax, a softmax output layer. This is the task-specific layer, specific to entity matching in this case. What is shown here is the in the center is the pre-trained language models such as BERT, but you can also use other transformer-based pre-trained language models. We fine-tune this model using training data for entity matching to adjust the weights of all layers. To train the model, we need to pass our training data through this model, which means we need to serialize the pairs of candidate pairs of records before passing through BERT. So how do we do that? So how do we serialize the input? So we serialize every record as follows. The attribute name will go after a special token, the COL token, and the attribute value will go after a VAL, a special token, the VAL token. So we do this for every attribute value pairs in the record to make it a sequence of tokens. To serialize the pair of tokens, this is what we do, right? We serialize the first entity as follows, followed by a special separator token, and the second entity followed by a special separator token. There's also a CLS token, which is there. So the serialized and tokenized output are passed through BERT. The CLS token here, which is the token that summarizes all the contextual information of the two records as a contextualized embedding vector, is then passed to the task-specific layers for prediction. Intuitively, this CLS token is expected to capture the representation of the entire sequence, which means both entities in this case, and can thus be used to decide whether the two entities match or not. The linear layer outputs a two-dimensional matrix for the softmax layer, which will return 0 or 1 for match or non-match. So by passing your training data, which are examples of pairs of records which are match or not match, through this model, the weights get adjusted to be a better model for the entity matching task. We are not limited to BERT here, right? So for any pre-trained language models, transformer-based pre-trained language models can be used. In fact, in our experiments, we use Roberta for better performance, and we use DistilBERT for faster prediction and training. As you can see, the architecture here is very simple, and for different applications, one typically only needs to modify the task-specific layers and change the way you serialize or tokenize your input to make this model work. This fine-tuned model itself already shows impressive performance, but Detour doesn't stop there. It also applies 3 optimizations to make it perform even better. The first is what we call injecting domain knowledge. which is to allow users to specify which information is more important. The idea is to highlight important information so as to help the pre-trained language model know better what to pay attention to. And by highlighting, I mean marking up the span of text. For example, if we know for products that the product ID is an important information to pay attention to, we may want to highlight the product ID with an open ID, closed ID tag, as shown here. We use spacey or regular expressions to identify and assign entity types. Other examples of what you may want to highlight for different domains are shown here. For example, for people, you may want to highlight the last 4 digits of the phone numbers, right, and or street number of addresses, and so on. We also normalize standard types. For example, put all phone numbers in the same format so that it becomes easier for the language model to understand what is the same or what is not the same. The second optimization we do is summarization. This is because pre-trained language models have a hard limit on the length of the sequence they can input. So if the length of the sequence of 2 records happen to exceed the hard limit, a lot of the tokens will be truncated, so that so in the case of entity matching, this means we won't be actually matching the 2 records correctly. To avoid this situation, to avoid truncation, we summarize the input sequence when needed. So one simple summarization strategy is to keep only tokens with high TF-IDF, and this is what we have implemented in Ditto. The third optimization we do is data augmentation. This is done to reduce the amount of training data, labeled data that we need. In the data augmentation process, we apply different operators to create more training data. For example, by dropping a span of tokens, removing 1 attribute, or swapping the order of 2 attributes. By reordering the attributes and values, we are actually also teaching the model to learn that the order of the attribute values should not matter in this case in determining whether 2 records should match or not. Ditto also uses mixed DA, mixed data augmentation technique, which I won't explain in detail here, but the observation is that sometimes the data augmentation operators, such as the one that drops a span of tokens, can totally distort the result of entity matching. So what mixed DA does is to take the original token and the augmented token, the original text and the augmented text, which is the text which has a span of tokens dropped in this case, and generates an intermediate representation that is not too far from the original text, so that this is has a less likelihood of creating a distorted result. So we experimented Ditto on the following 2 benchmarks, the ER-Magellan benchmark and the WDC product benchmark. ER-Magellan has 13 data sets in total in 3 domains: publications, products, businesses, and in 3 categories: structured, dirty, textual. The WDC dataset is a much larger dataset with more than 200,000 product pairs in 4 categories: computers, cameras, shoes, and watches, and in 4 sizes from small, medium, large to extra large. In the experiments, we compared Ditto with Deep Matcher on the F1 score and training time. We also ran Ditto on a real company matching dataset. So here are the results for the ER-Magellan dataset. So the size column shows here the number of candidate matching pairs, and Ditto is uses the Roberta pre-trained language model in this case. And then here's the column for Deep Matcher. So the first thing to observe is that Ditto consistently outperforms Deep Matcher, and in cases where the data set may be small or noisy or text heavy, right? So in this row you see here, we have a small number of candidate pairs, which means we have less training data for Ditto to fine tune it, right? So in this case, Ditto outperforms Deep Matcher by quite a bit. These two rows here in orange shows that Ditto is also more robust in cases where the data is noisy, small, or text heavy, right? So, and the performance gap can go up to 32% in the F1 score in some cases. The results for the WDC dataset show a similar pattern. Observe that Ditto already outperforms Deep Matcher with half the amount of training data. So, for example, with about 9,038 labeled data, Ditto's F1 score is 84.36, and this is already more than the case for Deep Matcher, with about 25,000 amount of training data. We also conducted ablation studies to determine the effectiveness of the optimizations we applied. Here are the results. DA means data augmentation, DK means domain knowledge. The Ditto column has all three optimizations applied. Ditto DA means only data augmentation applied, and DK means only domain knowledge applied. So the baseline has no optimizations applied. You can see that all three optimizations are effective, and in all cases, and some optimizations are better than none in general. We also applied Ditto on two real-world company datasets, which are much larger than the benchmark dataset shown earlier. There are about 800,000 and 400,000 entries in these datasets. An example of what the records may look like is shown here. Ditto can achieve an F1 score of 96.5% in this case. To match company records, we have to implement the complete pipeline to include not only the matching phase, but also the blocking phase. Ditto, which is what I've described so far, is shown in this box here, right after the blocking function. In this pipeline, the first step is to construct a blocking function, which is typically implemented using heuristics such as keyword matching. After this, we sample and label a training validation set, which is then used to train the Ditto matching model. Optionally, the labeled dataset can also be used to train a deep learning model for blocking, and we call this advanced blocking, and that's what we have implemented for the entire pipeline with Ditto. In terms of related work for entity matching, there is a long list, and I list only the more recent ones here. There is concurrent work on applying transformer-based pre-trained language models by Brunner and Stockinger in EDBT 2020. They applied pre-trained language models without any optimizations, and that's identical to Ditto's baseline without any optimizations. There is also entity matching solutions based on recurrent neural networks, hierarchical-based deep learning solutions, and the ones that use transfer learning and active learning to alleviate the steep requirement for training data. I'd like to give a shout out to the work on data augmentation, which is appearing in this SIGMOD by Zhengjie Miao, Yuliang Li, and Xiaolan Wang. There are a long list of other works, but very recently there is a book titled The 4 Generations of Entity Resolution by Papadakis et al. That gives you a good overview of the evolution of solutions over the past few decades for entity matching. Deep learning methods have also been successfully used in many other data integration tasks, such as information extraction, whether it is about extracting named entities or relation extraction or opinion mining. They have all been reported to have achieved very good results. They have also been applied to table understanding, data curation and preparation tasks, and querying tables and text, and they have all reported to have achieved really good results or very promising results. At this point, I want to take a step back and discuss why I think deep learning models have been successful at various data integration tasks. First, deep learning is especially good for tasks where rules are difficult to specify and features are hard to engineer. And many data integration problems are like this. For cases where features are hard to engineer, this is exactly what makes deep learning attractive compared to traditional machine learning techniques, which often require extensive feature engineering. And for tasks such as information extraction, entity matching, table understanding, these are exactly tasks where it's difficult to write rules to solve these problems. In entity matching, for example, it is difficult to write rules to cover all cases of when two records should match or should not match, especially when schema can be heterogeneous and there can be variations in how concepts are described, and data can also be dirty. I should also emphasize that from the experiments of Dito, demonstrates that deep learning is really good at dealing with data imperfections, whether it's about typos, missing data, or wrong values. And that works because deep learning methods have immense capability to learn from examples. It has been shown that the lower layers of BERT, for example, capture more lexical structure, while the upper layers of BERT capture more semantic properties of a sentence. The deeper layers are also able to track longer distance linguistic dependencies. And it's through all these, it is capable of distinguishing the difference between phrases that are highly similar but yet different, for example, sharp TV versus sharp resolution, and at the same time also understand the similarities between apparently different phrases, for example, stop hair loss versus prevents thinning hair. I will also add that its immense ability to learn from examples and pay attention to the right details are also key here. This makes it capable of knowing what to focus on for different pairs of records. So for example, in the second pair here, it somehow knows to pay attention to the addition number, which is key in determining the unmatched decision here. And for the third pair of record, the model number is somehow important for determining the matching decision here. And if you think about it, this is exactly what a human worker will do if she's asked to make the decisions. She pays attention to different parts of the records for different pairs. So this all sounds too good to be true. So what's the catch here? As many of you are probably already aware, deep learning algorithms are data hungry. The quality of a deep learning model is directly dependent on its training data. And actually, the more training data you have, it tends to perform better. This slide here is taken from Andrew Ng's deep learning course. It shows that, first of all, traditional machine learning models perform performance plateaus when you have more training data, and that's shown by the bottom red line here. And the second point is showing here is that larger neural networks tend to perform better with more training data. So the yellow line shows the performance of a small neural network, and the green line shows the performance of a larger neural network, and the blue one is a medium neural network. So the more training data you have for large neural networks, the better it is. And if you, in cases where you don't have enough training data, it's actually not such a bad idea to use traditional machine learning algorithms in this case. I want to emphasize that the important thing here is not just to have more training data, but actually more quality training data. The more quality training data, the better it is for the deep learning model. And the irony here is that oftentimes obtaining quality training data for a deep learning model is a significant data integration problem of its own. Not only quality data, training data is difficult to obtain in general, one also has to be concerned about fairness and biases that may exist in training data. Deep learning algorithms also require higher performance hardware to work on, and they typically have longer latency and are more expensive to deploy in general. They're also more complex, right? They have more hyperparameters. The base model itself already has 110 million parameters, and I've lost track of how many parameters there are in the latest models these days. Deep learning models tend to be very opaque, right? It's hard to understand why it makes the decision it makes. And I should actually retitle this slide to say that these are disadvantages of using deep learning in general, not just for data integration. Going forward, I think there are lots of opportunities for the data management community. I believe we should put more effort to develop benchmarks for different data integration tasks. And these benchmarks should not just be about the data, but also include metrics for measuring the fairness of data. In developing techniques for data augmentation, one should also consider how data can be augmented fairly. There are also alternative methods to circumvent the data hunger issues, and that's through transfer learning, active learning, or weak supervision. And I've started to see some papers applying such techniques in the context of data integration recently. Another thread of work is model explainability, which is to be able to explain the results of your data integration outcome. For example, one idea is to generate structure, such as rules, which can be used to explain the black box deep learning model. I've seen some recent work on this for entity matching. Another thread of work attempts to directly explain a model's decision. For example, LIME works by finding parts of the input that led to a prediction in the output. I believe there is a lot of room for more work here. And for tasks such as entity matching, one is usually curious to understand why two records match and also why two records do not match. This is especially so when entity matching outcomes are used to drive decisions that can impact people's lives. We should also understand more on how to answer queries over heterogeneous data with different structure, different modalities, much like in a data lake. This is important as more and more data we face today and tomorrow will be outside the box, such as images, text, and audio. I'd like to bring your attention to the following ML Ops interview by Andrew Ng, recently in March 2021. In that discussion, he encouraged people to take a more data-centric view of AI than a model-centric view of AI, because there is better chance of improving the overall performance of a model if one improves the quality of data. I put here two quotes from that discussion. In the first one, he says, when a system isn't performing well, many teams instinctually try to improve the code. But for many practical applications, it is actually more effective to instead focus on improving the data. In the second quote, essentially, he's saying, all things being equal, the quality of the data is what differentiates your model from another team's model. Finally, this is my last slide. I'll end with this question on whether we can do data integration for social good. The world today contains a lot of content online that are multimodal. Content can be a piece of text, an image, audio, or video, or combinations of these modalities. The world will be a better place if we can better understand the content we share or see online. One question here is, can we integrate data, well, broadly construed, to help better understand content? For example, can we find all duplicate contents and understand which is the original one? Can we bring additional knowledge to a piece of content, such as knowledge or the context of entities and the relationship between entities in the content? Or what might be the related contents with respect to this piece of content? Can we put all these information together to understand the meaning or intent of the content? And with these questions, I would like to end my talk by expressing my deep thanks to my co-authors of the Dito paper, Yuliang Li, Jingfeng Li, and Yoshi Suhara from Megagon Labs, and An Haiduan from University of Wisconsin. They gave me lots of feedback on my slides, and some slides on entity matching are originally from Yuliang Li. I would also like to thank Alon Halevi, who gave me feedback on the slides as well. And with this, thank you for listening to my talk.
So let's start by thanking Wang Chu for a very interesting and informative talk. And as you have questions, for Wang Chu, please type them in the Q&A box, as I've mentioned, if you're an attendee. And if you're a panelist, please raise your hand. I see that Guoliang has already raised his hand. So Guoliang, please go ahead and ask your first question.
Thanks, Manchu, for your nice talk. So I have two questions. The first question is that it seems that did you work on single domain? So whether it can be extended to support, for example, multiple domains like GPT-3. So for example, we can a big model, large model that can support a different domain for entity matching. This is the first question. The second question is that can we extend the model to support other data integration tasks? For example, whether we can merge the record after entity matching to generate a golden record, or can we use it to clean the data, or to, for example, add some meeting data from other records? So these are my two questions. Thank you.
Yeah, so these are great questions. So for the second question, whether you can apply deep learning models to say merge records or clean data, I've seen some papers starting to work on this front. You likely need more of the sequence to sequence type of deep learning models to be able to generate a merge record, right? So maybe you need to fine tune those models to understand how to merge first before you apply them to merge generally. So yeah, and also for data cleaning, yes, I think the answer is yes, but again, you need to show it enough examples of what data cleaning means. As for your first question of whether you can apply Ditto to different domains, you do need the labeled data to fine tune them right now. I'm not aware of a generic technique right now that can be versatile enough to run it off the shelf for different domains and perform well at the moment. Yeah, I hope this answers your question.
Yeah, thank you. Thank you so much.
Yeah.
Thank you, Wang Chu. Next question from Felix.
Sure. So thanks, Wang Shu, for the very nice talk. I'm going to show it to my students, the video. It's really, really very good. So I have one quick question. So I've worked with many people and companies, and when you show them results, they'll point to one false positive and say, why did that happen? And I really like the way that Ditto includes, some augmentation, and you can include a little bit of, let's say, show which spans are important, etc. But I'm wondering how we can, we as a community, or maybe Ditto even, can span all the way to rules, right? Because in the end, I guess experts are itching to write a specific rule for their special cases, right? So I'm wondering if we can, have the whole range from purely learned techniques to rule-based techniques, and how that could fit into Ditto.
Yeah, I would like to signal boost what you said, right? I agree with you completely. It would be nice to have a range of techniques going from black boxes to rule-based techniques. And my take is that for sensitive applications that drives decisions to that will impact people's lives, chances are you will need explanations to be in place. Either a human will still come in a loop and try to understand why a match is considered a match or not, right, before the decision is given out, or you need rules to be able to drive these explanations. I don't see a way out of that right now, right? But yeah, but who knows in a few years' time. So yeah. But I totally agree with you. It would be nice to have this spectrum of techniques and interplay, actually.
Okay, thanks.
Thank you, Wang Chu. So we have a question in the Q&A box. So Omar Huselma has a question. Let me see if I can, let him ask the question himself. So Omar, are you there? Would you like to ask your question yourself?
Yeah, I don't see the question.
Hi, Deepesh. You want me to ask the question?
Yes, go ahead, Omar. You can show your video and ask the question directly yourself. Or I can ask the question on Omar's behalf. So the question is, because deep learning is data hungry, what would be a best practice approach to apply deep learning techniques in the context of data lakes, or more generally in a virtual approach at query time?
Virtual approach at query time. So, so if the question is about how to mitigate data hunger, right? I think there's a lot of progress these days on using transfer learning or data augmentation or even zero-shot ideas, right? If the question is about how to answer queries over data lake using deep learning techniques, I must confess I don't really know how to answer that question, but it's a direction we should all move to. In the NLP community, there is a lot of QA techniques for answering over text data, right? But we do need to be able to answer over, you know, not just text, but, you know, data that may be in a relation or even images. So how do we do all this together, right? So that's one question. Yep.
Thank you, Wang Chu.
Yeah.
Any other questions for Wang Chu? So let me ask one question as chair first, and then we can give the floor to others. You mentioned, you know, sort of this quote from Andrew Ng, right, talking about the importance of data even more than the importance of code, right? So all these pre-trained models that you're working with have been trained on large corpuses of text, right? But if you look at most data integration problems, the data doesn't consist of large corpuses of text, right? You know, it contains all these abbreviated text, short text. Do you have a sense that, you know, if you were to train, you know, these pre-trained models on some kind of a different corpus, I don't know, maybe take all the databases that have been, you know, created in the last 50 years, right? Encode them using the approach that you have and somehow use that as a training, would it or could it lead to something more interesting, something better?
Yeah, I'll point you to the whole list of work on table understanding. People have started to try to train a bird-like model for tables, right? And exactly using this idea of, you know, let's take as many tables as we can, and let's train based on this corpus of tables and see what we have. So that's a direction that the community is heavily investing on, and I see many cool results. I think I even gave references to some papers this year. But I want to also emphasize again the data side of what Andrew Ng said. And in fact, I think just a couple of weeks ago, he released a competition, a data-centric AI competition based on you know, improving the quality of data to get your models better. So I can't emphasize that enough, because in the event where everybody has the latest, greatest pre-trained language models, what data you put in to train these models is what you get from these results, right? The results you get is what you put in to train these models. So I can't emphasize that enough. And these days, there's a lot of push to understand also issues such as fairness and biases in the training data. And that's very sensitive, of course, even for applications that may not drive decisions that will impact people's lives, but may influence how you think, right? So, yeah.
Thank you, Wang Chu. Any other last question for Wang Chu before we close today's session? Felix?
Just I mean, from the very high level question, just a very quick note. What about numeric data? I mean, you mentioned it briefly, and I think the vast majority of data that I've looked at that needs to be deduplicated is numeric, but we haven't touched it much in our community, I think. So what are your thoughts on this?
Yeah, very good. So yeah, I think we did need to do some more analysis on numerical data, but I do know that some of these tokenizers that come with these pre-trained models, they have their special tokenizers for numerical data that will tokenize them into sub-level tokens, which means they'll have smaller vocabulary and tend to interpret the numerical data better. But I have not firsthand, understood how well they perform. But certainly, this is a gap, especially for relational tables. We do have a lot of numerical data. Totally agree with you. Yeah.
Thanks.
So Wang Chu, in the Q&A, there was a question from Mei Hui, which was sort of, pretty isomorphic to what Felix asked about optimizations for numeric values.
Mm-hmm.
Let me just ask one last question. There is a question from Murad Ozani on asking, besides the challenges on things like explanation, heterogeneity, etc., do you think there is room to improve existing DL-based ER techniques from, what we have accomplished in DITO?
Yes, lots of room. I think explainability is an important, very important direction. You don't just want to use the results, from your deep learning model to drive decisions. It's very important to be able to understand why these decisions are made. And I think I didn't emphasize it enough, maybe, especially if two records don't match, you want to understand why they don't match. Okay, it's not just why the two records match, but you want to understand why they don't match. And think of sensitive matching questions like matching jobs to applicants. You do want to know why, certain jobs are not matched to certain applicants. So this is a more important question in understanding why a job matches an applicant, in my opinion. Right. So, yeah.
Thank you, Wang Chu.
Yeah.
So I think, there's a lot of questions which we can take offline.
Mm-hmm.
We should close the session because there is another session going to start. So let's all thank Wang Chu again.
And thank you, everyone. And thanks, Divesh, for staying up so late to host this session. And I'm happy to take the questions offline. Just reach out to me. Yeah.
So for anybody who needs more questions or ask questions, there is another instance of this talk coming up in 11 hours. So please join again and ask your question then. Thank you, everyone.
Thank you.